Welcome back to the next chapter in the Siemens KNX basic training, the chapter System Overview. As the name says already, it is supposed to give you an overview about the most important technical features of the KNX system. So you will find most of these pieces of information also distributed in the other chapters, but more detailed. The individual topics here are addressing modes, steps of project design, to-do checklist, communication objects, user information in a bus telegram, interworking, data point types and function blocks, twisted pair bit data transmission, collision treatment, method of signal transmission. We return to our KNX bus in a nutshell, as we have started in the chapter Installation. A push button, an actuator and a bus power supply. As a reminder, the picture of this assembly once more.
Let's enter the required addresses. At first, we need the individual or physical addresses of the devices. You also see the correct annotation, which is used in ETS. 3 figures separated by dots as delimiters. So we have assigned 1.1.1 and 1.1.2. Remember the sequence in the 3 figures: area, line, device number. For the function switching, a group address is created. For this example, the 3-level annotation has been chosen. Later, we will learn 2 more formats, but in all 3 cases, the group address is 16-bit long. To distinguish it from the individual addresses, we use the delimiter / between the 3 figures. Our sample group address is 1/0/0, or just short 100. You can see that we have 2 individual addresses, but only 1 group address, as this is shared by the devices controlling the same function. Practical example. This is how it works. If the upper rocker of the single push button 1.1.1 is pressed, it sends a telegram which contains the group address 100 and the value 1, as well as miscellaneous data. This telegram is received and evaluated by all connected sensors and actuators in the same line simultaneously. Only the devices with the same group address send an acknowledgement telegram, read the value and behave accordingly. In our example, the switch actuator 1.1.2 will close its output relay, switch on, because it is also linked to the group address 100. Series connection in KNX technology. If you are an electrical installer, you know the meaning of a series connection. To operate 2 separate circuits from one place, 2 switches are required in one box. The loads are separately wired to them. In KNX, it is as simple as this. Use a twin rocker switch, 2 group addresses, and an actuator with at least 2 outputs. The group addresses will be linked, like before, to the corresponding sensor and actuator communication objects. Sample: Channel D on/off from several buttons. This example shall clarify how the control of an actuator channel is made correctly from various control points and with various group addresses. Channel D of the switch dim actuator on this picture is assigned to 3 different switching groups. The central group, B1 central switching, which means all lights in building 1 central switching. Group address 1512. The group F1 central switch, which is all lighting in building 1 floor 1 switching, group address 200. And finally, the single control function F1, R1, L1 switching, floor 1, room 1, light 1 switching, group address 100. For each of these three groups, another operation element is required. In our case, we have three single rocker push buttons. The groups are linked to the corresponding objects of all subscribers, actuator and sensors. What are these objects? Actually, they are nothing else but a place in the memory of the bus device. They can be between 1 bit and 14 byte large. The size depends on the function. Switching requires only two states, 0 and 1, and so a switching object, like in our sample, is 1 bit large. A 14 byte large object, by the way, is used usually for short text messages. To establish a function, ETS must link the objects to the corresponding groups, or vice versa. Only objects of the same size can be linked to the same group address. Anything else would be nonsense. An object can be assigned to several group addresses, as we have done this in our sample with the actuator. Only one of them, however, can be used to send messages with the information stored in this object. Therefore, it wouldn't work if one would assign all single function groups to the object of a push button. So always bear in mind this very essential rule. Every function group requires its own group address. This rule, by the way, is also the only reasonable one. Just imagine what would happen if a push button has to control 1000 channels as a central function by sending 1000 individual telegrams. This would jam the bus for at least 20 seconds. Nothing else could be done in this period. Therefore, such a function is realized by assigning the same group address to all 1000 actuator channels, so that the transmission of just one single telegram would switch them all simultaneously. Another remark as for the communication objects. They are alternatively also named group objects. This name is self-explanatory. Sample channel D toggling together with other group functions. Now we talk about the listening function of sensors. Group addresses at second place or further behind in an object have a listening-only property. That means the sensor will read the value change and so update its own status when receiving telegrams on these listening addresses. In our sample, sensor 1.1.2 is a toggle button. When operated, it will always send its inverted object status. It also receives the value changes of the central function sent via group address 2/0/0 or the group function sent via 1/5/12 and updates its status. This link is necessary to avoid button operations with no effect. Group addresses and functions. This table shows the most used functions, their control values and lengths, and the resulting value ranges. You can recognize that none of them is larger than 8-bit. These functions all refer to the controlling and reporting of binary information, like switching and Boolean operations, especially all lighting controls, like dimming and value, and solar protection controls. Central combined binary functions are also covered, like all lights off, all blinds up together. As already announced, now more information about the topic group addresses. The base for it is a 16-bit large addressing field. It has the same length like the individual address, which is reasonable when you later look at the telegram structure. But as for the functionality you want to control by the group addresses, the value doesn't matter, only that the corresponding sensors and actuators are always linked to the same group address. These group addresses are thus completely free to use. If you decide to create your very own address structure, you can do that with what is called the free structure. This option, however, is available as from ETS4 and higher only. In the beginning of EIB, the predecessor of KNX, an arbitrary structure has been set. It started with the two-level structure in ETS1. It has 32 main groups with 2048 subgroups each and can still be used in the current version of ETS. When ETS2 was launched later, the three-level structure was introduced. It is distinguished by the further splitting of the subgroups into 8 middle groups of 256 addresses each. The bit grouping in this structure is 538, which is different from the individual address with 448. There is one special group address which cannot be used for normal operation. It is the 0 address. It is called the broadcast address. It is used by the system to assign individual addresses. This image shows the three-level group address structure in ETS5. You can see the colors for the distinction of the three levels: main groups blue, middle groups green, and subgroups red. Structure of group addresses. If group addresses are used in the three-level format, there is a certain recommendation how the structure should look like. It is of course not mandatory. Because there are up to 32 main groups, they shall correspond to the floors of the building, starting with 1 for the lowest floor. Therefore, up to 31 floors can be distinguished. Main group 0 shall be designated for global functions, used for the whole building. The restriction is, the maximum of group addresses for one floor is 2048. Middle groups are encoded by 3 bits, so there are 8 of them available. Again, it is recommended to use middle group 0 for central tasks. 7 more middle groups of 256 subgroups each remain for the regular controls. They shall be assigned the different traits, like lighting, sun protection, or climate control, which are usually always used. More middle groups could be assigned to safety and security and to energy management. 2 blocks of main groups. Main groups as from 14 and up cannot be used with old line couplers. Old means they must have been assembled before the year 2004. They had only limited memory, which was good for 14 main groups. The new generation of couplers was upgraded with sufficient memory, so with them the whole range of group addresses is usable. The number of group addresses which can be assigned to the sensors and actuators depends on various factors: the system profile of the used bus couplers, the amount of memory, and the type of application program. There are no other restrictions. As for the available number of group addresses versus the required number, it becomes more and more difficult nowadays to stick to the three-level structure. Function design requirements demand more and more group addresses per each actuator channel. While in earlier times just 2 group addresses were sufficient to switch and dim a light, we have now at least 5 or 6 resulting from the object for value control, 2 status objects for switching and value status, and an object for hardware defect reporting. Modern solar protection actuators have even more, if they are integrated in an automatic system controlled by weather centrals. The biggest number of group addresses are required by climate controllers for heating, chilling, and ventilation control. Compared to them, 256 group addresses suddenly become quite a small figure. In this case, it will pay off to use the free address structure, because ETS offers free-scaled containers here. Especially the address containers for central controls would be much smaller, so no group addresses would be lost by the rigid tree-level structure. Sequence of configuration steps for devices. Search the catalog for the required device. Before you do anything else, you must make up your mind what product you will use for a certain function. Select the appropriate application software for the chosen device and insert it in your project. Some devices may have several application programs. Make sure to choose the best suitable one. Do the parameter settings for the selected application before assigning group addresses, because the parameters rule the visible objects. Assign group addresses in order to realize the desired functions. These group addresses should have been created before, but creating them while going through the objects is also possible. If not already automatically set, assign proper individual address now. Steps of project configuration. You can use this paper like a checklist in order not to forget something and to do everything in the correct sequence. The steps of device configuration are of course embedded in the project configuration steps. Before you can insert any devices, the project must have been created, and for the sake of a clear overview, a building structure must have been established. The building structure consists of floors, rooms in the floors, and switchboards in rooms. Staircases also have to be created, as they are floor crossing. Then you can fill up the building structure with the required devices, following the configuration steps as shown before. The topology also has to be established as appropriate. Please refer to the chapter Coupling of Lines to see a sample how to establish a reasonable topology in a building structure. When you create the topology before inserting devices, you have the option to assign all building view elements already to the lines. Whenever inserting now bus devices, they will automatically receive a suitable individual address. When the project is finished, the commissioning phase starts. In this phase, you download all devices and run the function tests. User data in a twisted pair bus telegram. Let's proceed to a new topic, the bus telegram as it is used on the medium twisted pair. We begin with the three most important parts of it, the two addresses and the user data. Compare it to sending a letter or an email. To convey data, respectively user information, to a destination, the destination or target address must be clear. In KNX, destination addresses can be individual or group addresses. The individual address is, as we have learned already, only required for commissioning and diagnostics. The normal operation mode is covered by the group addresses. Still, in each telegram, a physical address is included. It is the source address, the address of the sender. It is important for tracking back messages in case of troubleshooting. Next to other administrative information, the user data finally are the most important parts of the telegram. They tell the final receiver of the message what it has to do now. To save time when transmitting short data blocks, which may be as little as 1 bit, a flexible telegram structure has been created, where the length of the user data is variable from 1 bit to 16 byte. It must be added that sending of shorter data blocks than 1 byte isn't possible in the KNX telegram structure. It depends on the receiver to filter the relevant bits from the user data if shorter than 1 byte. Also, the maximum length of the useful user data is not 16 but 14 byte. The reason here is that the receiver also needs control information about the usage of the received data. The first 2 bytes of the user data are this control information. This must not be mixed up with the control field at the start of the telegram. More details you will learn in the chapter Bus Telegram. Standardized data point types. As already pointed out in the chapter System Arguments, one of the most important success factors of KNX is the standardization. This applies, of course, also to the format and interpretation of the data transmitted in group communication. In this table, you see a small choice of the most common data point types for switching, dimming, and blinds control. Data point types have been developed to guarantee the compatibility of function identical devices of different manufacturers, for example, dimmers and clocks. The data encoding describes the format and structure of communication objects, both for sensors and actuators. The combination of different data point types is called a function block. Please note also, data point types do not reduce the freedom of the individual manufacturers in application development, since they do not prescribe certain parameter settings. In communication technologies, there are always 2 issues to be solved when transmitting data. First, what shall be the length of the data? The length determines the value range. Example, 8-bit data can have 256 different values. Second, the interpretation of such values. The 8-bit values can be standardized to a range of 0 to 100%. The formula is: each original value between 0 and 255 must be divided by 2.55 to get the required value range. The KNX Association has invented a classification system like follows. Data point types are numbered like XXX.YYY. The figure XXX before the point describes the main data point type. In our picture here, it is the binary data point type 1 with the values 0 and 1. The figure YYY after the point describes the interpretation. With binary types, it is always the effect of either 0 or 1. The DPT 1001 switching describes that 0 means switched off and 1 means switched on. The same combination for Boolean values means 0 equals false, 1 equals true. Both data point types 1001 and 1002 are understandable with common sense. DPT 1003, however, can be mutually interpreted. It describes disable and enable. Here it is really important to have a fixed rule being mandatory for all manufacturers. 0 means disabled, 1 means enabled. Where can you see which data point type is applicable for a certain function? Well, it is in the properties of each communication object. There it is either already configured by the manufacturer of the application program, or you can set up this property on your own as required. DPTs are, as pointed out, only an interpretation of data. They are nothing which has to be downloaded into a bus device. Therefore, the properties data point type are fully accessible by anyone who configures the bus device. Parameters of the respective bus devices that modify the effect of an object are also not part of the DPTs. Example, inversion. This allows a normally open contact to be turned into a normally closed contact. However, this does not change the DPT of the corresponding object. Function block, shutter and blinds actuator basic. If several subfunctions are required, or at least desirable, for a particular function, then this grouping of subfunctions is called a function block. In this example, we have the function block drive control. Venetian blinds, roller shutters, window regulators, 3-point valve actuators, etc. require a stop function in addition to a travel command that goes in two directions, as we have already discussed in the chapter Bus Devices. The question was, what should be the data point type look like? It was agreed to make it as easy as possible and, above all, to make it compatible with other functions. Therefore, two data point types have been defined: the up-down type 1008 and the step-stop type 1007. Sometimes you can also read that type 1009 open-close applies. However, this does not correspond to the KNX standard. By setting this to two 1-bit types, it is also possible, for example, to connect lighting control switching with the opening or closing of blinds via a single group command. Light off, blinds up is the same value, a 0 in a 1-bit telegram. Function block dimming. The dimming function block is binding for dimming actuators. It consists of a DPT 1001 switching, a DPT 3007 relative dimming, and a DPT 5001 value control 8-bit. Sensors, on the other hand, are not affected by this regulation. With the relative dimming object DPT dimmer step, the dimming actuator receives a dimming command relative to the currently set brightness. The highest value of the 4 bits is the sign, so to speak, the dimming direction. 1 means brighter, 0 the opposite. The other 3 bits, the step code, represent a step size encoded as follows. The decimal value is used as an exponent for base 2. If the value is 0, this is the stop command, as we have already learned in the chapter Bus Devices. All other values from 1 to 7 lead to the following values: 2 to the power of, in brackets, step code -1 equals number of steps to achieve 100% change. 2 to the power of 0 equals 1, and this is the already treated start command, step size 100%. 2 to the power of 1 equals 2, that means 2 steps at 50%. 2 to the power of 2 equals 4 times 25%, and so on until you get the smallest step size. 2 to the power of 6 equals 64 times 1.5625%. DPT 5001 Scaling. The DPT 5001 Scaling describes an unsigned 8-bit value that is normalized to a maximum value of 100. To show that it is a ratio to the respective maximum value, the percentage sign is added. This means that almost all analog parameters can be represented with this DPT, if they are to be displayed or controlled relatively. It doesn't matter whether a luminaire emits 1000 lumens or 350 lumens. If you want to have half the luminous intensity, you send a 50% command to the actuator. The resolution of this DPT with approximately 0.4% is also sufficient for lighting purposes. This DPT is also used for the direct positioning of blinds or motorized actuators for heating valves. 2-octet float value, data point type 9000XXX. The DPTs of the main group 9.xxx floating point have a length of 2 bytes. They are used for everyday physical measurements such as brightness, lux, wind speed, meter per second, kilometers an hour, all temperatures, current, voltage, power, and much more. It's a calculated data point type. It is therefore not possible to simply enter the 2-byte values as a hexadecimal number into the calculator and convert them to decimal numbers. The result will always be wrong. But if you want to do the conversion yourself, you have to split the 16-bit in sine 1-bit, exponent 4-bit, and mantissa 11-bit. However, the ETS translates the values correctly in the group monitor during telegram recording, so that these explanations are only informative for you. Communication flags. Whether a bus subscriber is allowed to communicate with other bus subscribers or not is determined by the so-called communication flags. Communication flags are individual properties of group objects. They can be set differently for each object. There are always at least the 5 flags shown in this image. Newer bus subscribers can also have a 6th flag called read at init. There are basically 3 different roles of the user functions, which are also distinguished in the settings of the communication objects. The C flag is common to all roles. C stands for communication. Its setting determines whether the object in question can receive data from or send data to the bus at all. If it is deactivated, it works like pulling the plug out of the socket at home on your phone. The telephone line is disconnected. No one can call you, and you can't call anyone outside. Nevertheless, telegrams received by such a bus subscriber with deactivated C flag are always acknowledged when the target group address is in its address table. This is because there are different levels in the bus coupling unit. The first level checks telegrams for general consistency, and the next level checks telegrams for the destination address. If a suitable destination address is determined, an acknowledgement will be issued. That means an acknowledgement in the positive case. The application program is only on the 3rd level, and that's exactly what the flags are for. If the C flag is not active, the information must be ignored. The role Actuator. Here we see the minimum requirements for an actuator object. C flag and W flag must be set. The W stands for write and means that a received user data value can be written to the communication object assigned to the target group address. As a result of this, the application module can switch on its relay, for example. The role sensor. For sensors, for example in general all push buttons, binary inputs and physical sensors, C and T flags must be set. The T flag stands for transmit. If it is set, the device can transfer information from the application module as a telegram to the bus if required. If the button shown here in the picture is pressed, the object value is changed by the application module and thus by the application program. The bus coupler then sends the corresponding telegram. Comment on status objects. Most status objects of actuators are active today. This means that they immediately send changes in status to the bus. This is also a sensory function. However, status objects have also always set the R flag for reading. See next page. The role passive status. The 3rd main role in the flag settings refers to the passive status. In contrast to the active status, which represents a sensory function, the passive status is not transmitted automatically. It must be pulled, so to speak. Also for this there is a flag, the R flag. R stands for reading. For this purpose, the bus device must receive a specially formatted telegram, a so-called read telegram. Only if the R flag is set, the bus device will respond. In this case, it sends a reply telegram. Since a communication object can be connected to more than one group address, it must be determined which one may be used for the response, since an object may only send one telegram at a time. It is the first, or also called sending, group address in the object. In ETS, it looks like this. In the group addresses column of the objects, it is the group address on the far left. However, queries can be made with all addresses that are linked to the object. A very special case is the so-called U flag. U stands for update. The U flag was introduced primarily for the evaluation of response telegrams. It only works in conjunction with a set W flag. If a telegram formatted as an answer to a read request reaches a subscriber, its information is only transferred if the U and the W flags are set in the object at the same time. The most important application is that of a scene controller. The scene controller stores control values, for example, for controlling lighting with different dimming values at the touch of a button. If these scene values are to be changed, the scene push button sends a scene learning telegram. The scene controller in turn then sends read telegrams to the actuator status objects and collects the responses of the actuators afterwards. Attention if there are still bus couplers of the system 1 type in use. There was no distinction between U and W flag. The U flag is always active for bus couplers type 1 and can therefore cause considerable trouble if the group assignments are assigned in the wrong order. Here is a summary of the properties and effects of the communication flags. You may stop the video and read yourself. Congratulations! You made it again and reached the end of Chapter 6, Communication, respectively System Overview. See you back in Chapter 7, Bus Telegrams. Goodbye.